Okay, let's start. I am very happy to have here Anand U, who's a very good friend of mine and associate professor at the New Jersey Institute of Technology. He studied he did his bachelor studies at Princeton and then master's in Cambridge, PhD at MIT in applied mathematics, and then a postdoc in New York University, and now he's a professor in GMT. So he's talking about the working droplet system as a dynamic phenomenon. So,
Thanks very much. Thanks to Giuseppe for organizing all this. And thanks to all of you for coming. It's a real pleasure to be here. It's my second time in Calabria. So today I'll talk about some work that started when I was a PhD student, and that's how I came to know Giuseppe, on trying to understand this walking droplet system and its possible relationship to quantum phenomena. So I'll try to explain. What I mean by that. And this is kind of intended to be kind of overview. So I'm going to try to avoid some of the technical details, but I'm happy to discuss any of them if you're interested. I should also mention I'm on sabbatical right now at Imperial, so this was a easy trip, certainly easier than coming from the States. So we'll just get right into it. So this is the main object that we're going to be thinking about during this talk. I should say I'm not an experimentalist, so a lot of the videos that you are going to see were taken either by Giuseppe or by Dan Harris, this guy that his name will show up frequently in the talk. So he's a very talented experimentalist, currently a professor at Brown University. So we did our PhD together. So this is a droplet of silicon oil. In principle, this whole thing could work with something like water, but for experimental reasons, oil is nicer to work with. So there's a droplet of silicon oil, less than like kind of millimeter scale in diameter. And it's a little bit hard to see. Let me play the video again. But this is bouncing on the surface of silicon oil. So it's the same oil. And this whole bath is being shaken at about 80 hertz. So between, let's say, 50 and 100 hertz. So this video is being slowed down quite substantially, right? So this thing's shaking rapidly. And in this regime, this drop is bouncing at the same frequency as the forcing, right? So this thing is bouncing at, between 50 and 100 hertz. And you can see that as it bounces, it generates this depression, right? This kind of depression in the fluid. And really, what it's doing actually is that it's floating. It looks like it's making contact, but it's actually never making contact. It's floating. There's a thin air layer between the droplet and the bath, and it's basically kind of floating on top of that. So it's bouncing in that sense. So I'm not really. I think this is it's a beautiful like a kind of system, kind of in its own right, to try to understand, why is it bouncing? In what regimes does it bounce? This turns out to be a very robust phenomenon. So I think the experimentalists have had it bouncing for days before. So you can let this thing go. So it bounces without coalescing. So the intuition there basically is that, so if you look at like raindrops in a puddle, right? So we've all seen kind of a raindrop come and then coalesce into a puddle. In reality, in many regimes, what you get actually is that the raindrop comes down and then it bounces for a couple of times on the puddle very fast, so we can't see it, and then it coalesces. And basically, the process there is that you have a thin layer of air, like I said, between the droplet and the puddle, and that air layer needs to drain, and then that's the point at which you get coalescence. In this system, what's happening is because you're shaking, you never let the air layer drain, right? So the air layer essentially, before the air layer can drain, you kick the drop again, so it goes back up, and this process just keeps going, right? This, I think, is an interesting system by itself. I'm not gonna go into kind of the fluid dynamics of why that works. There's been a lot of work on trying to understand the bouncing and stuff like that, and that's kind of a topic by itself. What I'm more interested in is this regime. So this was originally discovered by Yves Couder, who Giuseppe worked with during his PhD, and Emmanuel Faure in Paris. So a lot of the early stuff was reported in this paper in Nature in 2005, and then there were a series of papers in JFM and European Physical Journal and many journals kind of after that following up. And they reported this interesting phenomenon where if you increase the forcing acceleration, right, so you shake harder, you'll see now that the drop started there, and kind of very slowly it moves, in this case, to the left, right? So what's happening there is that the drop is now generating these deformations like it was in the previous video, but now it's generating waves on the surface, right? And that's because of this enhanced forcing acceleration, and these waves cause the droplet to propagate, to move. And it's a symmetry breaking bifurcation in the sense that the system's isotropic, so there's no preferred direction. But once you have a perturbation that pushes the drop in one direction, then it sustains that direction and it keeps going straight. Right? So this is the walking droplet system, right? So you think of this thing as walking because it's bouncing and it's moving along. So just to kind of, I've set up some notation right here. So this is just to kind of set up the terminology. So I'm going to use XP to denote the drop's position in the plane. So this is in 2D, right? So there's an additional coordinate, that's the vertical position, that I'm not really going to think about too much during this talk. I'll allude to it where I need to. And I should say that what's happening here, kind of very qualitatively, is that the drop now is no longer bouncing at the same frequency as the forcing. It's bouncing at half the frequency. So there's a period doubling transition where if you shake the bath at 80 hertz, let's say, the drop then begins to bounce at 40 hertz, so half. And that, it turns out, so this is kind of a fact from fluid dynamics, that excites something called the Faraday instability. So the Faraday instability is something that arises in fluids when you shake a bath of fluid. And it turns out that the Faraday instability also occurs at half of the forcing frequency. So you have this resonance between the drop bouncing and this Faraday instability, and those are the waves that you see. But crucially here, the waves are really generated by the drop. So if I were to now grab the drop and take it away, then the waves would disappear, right? So basically you have viscosity, which kills the wave field. So the waves are there because of the drop, and the drop is moving because of the waves, right? So you kind of need the two together. So there's this thing called the Faraday threshold that I'll allude to. So that's the critical forcing acceleration above which you would have waves on the surface even if you didn't have a drop, right? So I'm not going to go beyond this number because in this system, I want the waves really to be generated by the drop, right? I don't want them to be generated by the forcing alone. Okay, so that's basically the setup, right? So basically I'm shaking, the drop is bouncing, and it's generating these wave fields. All right, so now I'm going to take a quick detour, sort of more for the benefit of if there are students here. So I talked about quantum mechanics in the beginning, right? So what am I talking about? So this is kind of a one-slide sketch about, of course, this is whole textbooks and courses to be given on classical and quantum mechanics. So of course I can't do that here. So I'm just going to kind of use whatever little bits I need. So the main thing is that, right, in classical mechanics, you have Newton's second law. So mass times acceleration equals forces, and these are deterministic trajectories, right? So it's an initial value problem for the position and velocity of a particle, given some potential v. This thing moves and it evolves, and then there you go, right? You solve this thing. And quantum mechanics says that this picture is wrong, right? At small scale, this is not what happens at the microscopic scale. And instead, you have this thing called the Schrodinger equation, right? So you basically say that you have and where this comes from is that there are two relations that have been confirmed experimentally. One is the energy frequency relation that I think most of us are familiar with, that the energy is proportional to frequency, and the momentum wavelength relation, that the momentum P is proportional to the wave number K, and proportionality constant in both cases is Planck's constant, h bar. And from that, basically, and this is essentially what Schrodinger did, in one line you get Schrodinger's equation. So this is a partial differential equation for the wave function, right? So you have d psi dt, psi is your wave function, and on the right-hand side you have the Laplace, so this is the spatial derivatives of psi, and if you have some potential v, you have some function v, right? And it's again an initial value problem, but now it's a PDE initial value problem, right? So it's a differential equation that you have to solve. What does it mean? This is, of course, what everybody, or not everybody, many people are worried about. Like, what is the meaning of this thing? So one way of interpreting this is that it is giving you, so quantum mechanics is inherently probabilistic. So it tells you, rather than telling you trajectories of particles, it is telling you expected values of different properties. So for example, the expected position is given by the first moment of this psi. Basically, psi squared is a density. So the first moment of that will give you the expected position. The expected velocity is given by something else, et cetera, et cetera. So basically, you can build observable quantities by doing integrals of this psi function, right? So that's kind of the standard interpretation of quantum mechanics. So you basically have these two worlds, right? You have this classical mechanics where you solve ODEs for trajectories, and then quantum mechanics where you solve PDEs, and then you take integrals of that to get whatever observables. And one kind of example that I'll come back to shortly, so I'll just go through it quickly, is quantum tunneling. So this is one of the standard examples that people do in first year quantum mechanics course. So you look for solutions to this problem in a certain simple geometry. So the geometry here is this, where you have some potential V that's compactly supported, so on some interval of length L, let's say, right? So the potential is V0 on this interval, and it's 0 everywhere else. And the picture basically is that you send in a plane wave, that's your psi1. It has incident A1 and reflected A1 prime components. It's transmitted on this end, right? So that's your psi3. And you basically ask, what are the solutions for psi1 and psi2, right? So the solutions on this side and the solutions inside the potential and psi2, right? So basically, what is the solution to this problem of a plane wave incident on a potential barrier? Now, in classical mechanics, this problem is not interesting, right? You basically say that if your potential barrier is too high, so if your initial energy is too low, you bounce off. Otherwise, you can go through the barrier, right? Quantum mechanics says something weird. It says that that's not true. So even if your initial energy, the energy of the incoming wave, even if it's less than V0, you find that there's some non-zero probability of having an A3, right? Of having a transmitted wave. So this basically says that even if you're coming in quite weakly, there's going to be some small probability, exponentially small probability. So the equations don't matter here, but basically the key is that you have an exponentially small probability, but non-zero, of having a wave in this region, right? So this was kind of one example in which the wave nature of particles kind of differs substantially from the particle picture of matter, right? Because the particle picture would say that you can never go through, but the wave picture says that you essentially have this evanescent wave that you can observe, right? So that's just one example in which quantum mechanics is a bit strange, right? A bit counterintuitive, if you'd like. So one of the early, let's now go back to the drops. So one of the early examples of the drop system behaving like this was in this paper by Yves Couder in 2009 with Anton Iadi and Emmanuel Faure. So I don't know if you can see, this is the drop right there, and this is a barrier. You have a square barrier on all sides. And basically, if you look at what this thing is doing, it's behaving kind of like a billiard ball, right? This thing kind of, the drop wanders around, it hits the edges, it reflects off the edges. And the way to think about what's happening is that you have inside this, you can think of it like a cavity. You have a cavity with a deep region. It's got some depth h0, and then on this boundary, on this barrier, you have a shallow region h1. Right? So it's like a thin layer of fluid that's above this wall. And what's interesting about that is that this drop, you basically tune your parameters so that the drop can walk inside there, but it cannot walk on there. Right? So this you can do in the experiment. So they took various measurements, and here what this is showing, so the horizontal axis here is the depth of the bath. The vertical axis here is the forcing acceleration required to make the drop move. And you can see basically that it's this monotonic decreasing function, right? So if the depth is too small, you need a very large forcing acceleration to make the thing walk. So in this parameter regime in which this video is taken, the drop actually cannot walk on that region. So basically you have this situation where the drop can move inside, but it cannot move when it gets near the barrier. So the question is, what does it do after a long time? And what they found is actually the drop does sometimes cross the barrier unexpectedly. So basically, you do the experiment for a long time. Most of the time, the drop does what I showed previously, that it just kind of bounces off. But occasionally, it gets through. It tunnels, if you'd like. This is of course not quantum tunneling, because this drop is huge, right? You can look at it while this is happening. But the data is interesting, I think. So what you get is, so for example, you can look at the horizontal axis is the velocity at which the drop is moving, that you can tune by changing the forcing acceleration. And the vertical axis is essentially the probability of the drop exiting the cavity. And what you find is that as your velocity goes up, the drop has a greater probability of getting through, which kind of makes sense, right? It's the drop's moving faster, it can get through that region, even though it shouldn't be able to walk there. Similarly, you can ask, what is the probability of exiting? That's the vertical axis here, as a function of the thickness of the barrier. And there, again, you have quite a bit of error, but you have this kind of decrease in the probability. So if you have a thicker barrier, you have less probability. So the idea basically was that, again, kind of similar to quantum mechanics, you have this probabilistic behavior, probability in the sense of long time, right? You basically have to let the experiment happen for a long time. And then there are sort of these randomish events that happen that cause the drop to tunnel through. And this probability increases with the speed and decreases with the barrier thickness, right? So this is kind of qualitatively like quantum tunneling, but this is happening in a macroscopic system. So this was revisited recently, and I would say that this problem has not really been closed. I think it's fair to say. So this originally was found in 2009. There's this paper from 2020 from John Bush's group that tried to really look at what's making the droplet tunnel, right? In quantum mechanics, you can't even answer that question because there are no trajectories to speak of, right? So it's all kind of probabilistic behavior. But in this droplet system, you can ask, why is it doing that? And I think we still don't really know. So what they did here is they looked at an ensemble of trajectories. Here, this is the distance from the barrier. The barrier is right here. So here, imagine just a one-dimensional, like a wall, basically. And the vertical axis here is the velocity with which the drop is moving. So you basically send a bunch of drops here that way, and then you basically end up with two families of drops. Some of them in red get through, and most of them, the black ones, get reflected off and they go that way. But the strange thing is, if you look at this, it's a little bit hard to see here, but the inset here, this shows this region of the trajectory. And if you look at, basically the data points are kind of scattered in the sense that it's very hard to predict which one of these trajectories will eventually get through and which ones will not. Right? So there seems to be some kind of strange thing is happening far away from the barrier that somehow dictates whether the droplet eventually gets through or not. And in this paper, what they said is that there's some slight modifications in the bouncing behavior that determine whether the drop goes through or not. But I would say it's not clear really why. But the important part is in this paper, they recovered this probabilistic behavior, whereas you change the forcing acceleration, you get, at low forcing, there's zero probability of getting through. And then as you get closer and closer to the Faraday threshold, the probability goes up, right? So you have this kind of analog tunneling. So that's one. There's another really nice experiment. This was done in John Bush's group. So this is a video taken by Dan. So this is the analog of a corral. So the idea here is to, instead of letting the droplet move in a large domain, you now confine it. So I don't know if you can see, there's a dish, basically. You can see the outline of a dish. So this is, handful of wavelengths in diameter. So you're basically confining the motion of the drop. Okay, so that's the experiment. What do you get? So this is a video that was taken, so this is an experimental video. So this is a video of the experiment where they've color-coded the trajectory by the speed. So blue are regions where the drop is moving slowly, red is moving fast. It basically looks like spaghetti, but maybe you can see after a long time, there's some kind of structure here, right? So the motion at intermediate timescales is chaotic. It just kind of looks like nothing. But if you look after a long time and you ask the question, what is the probability of finding the drop in a given location? You get something that's quite nice. So basically, you get this kind of probability distribution function that's peaked at the center, and then it has oscillations, right? So there's one region, another region, where you have regions of large probability where you're likely to find the drop, and then you have regions in between where there's very low probability of finding the drop, again, after a long time. And this was very exciting because there have been experiments like this for electrons in the so-called quantum corral. So there you take your electron, you surround it by negatively charged ions. That's these little pills on the outside. And then you can measure the probability, essentially some kind of wave amplitude, of finding the electron in different places, and you get this kind of ring-like shape. And this was an exciting experiment because this was like a confirmation of Schrödinger's equation. So you can show, or at least what they showed in this paper, is that the distribution that you get is essentially a solution to Schrödinger's equation with the appropriate boundary conditions. Yeah.
Walker's experiment is ergodic.
Ah.
If it's not ergodic, that's not going to be
okay.
Right foundation. Okay.
That's right. So I would say the assumption is that it's ergodic, and it seems to be. So I think from the experimental point of view, what they did is I don't remember how, this was quite long. I think it was maybe like 30 minutes or something, right? Yeah, so it's quite long. And I think then they did another experiment where probably not double the time, but they took a longer time. And then the statistics didn't really change. So which kind of tells you that it's probably ergodic. Yeah. 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 So that's one of the challenges in the experiment that you need to let it go for a while. Okay. So I'll just say I want to focus on the Walker system today because that's really I'm not an expert on quantum mechanics by any means. But I'll just kind of say what what one possible goal of this endeavor could be. So there's been since the writing of quantum mechanics, there's been an interest in kind of understanding what does the theory mean at kind of a fundamental level. And very early on, Louis de Broglie and then later David Bohm, they proposed various versions of something called pilot wave theory. So actually what they proposed was a little bit different. So, but I won't go into that. So I'm just going to kind of lump them into one thing, even though that's not quite right. And one version of the theory is to basically say that you actually do have particles, right? So for example, electrons. Electrons are particles, but they are driven by the solution to Schrödinger's equation, right? So psi is the wave function that I introduced before. And basically, so you have mass times, in this case, you have this first order equation. So the momentum of this particle is given by this, the phase of the wave function, basically. Eventually, though, this was, and I think there's kind of a whole story here, that the Copenhagen schools, this is Bohr, Heisenberg, and others, basically said that this is not the right way to think about it, or at least it's not necessary to invoke particles because you can get all the predictions from even assuming that the particles aren't there, right? That the fundamental thing is the wave function. And this is the Copenhagen interpretation, which we, at least in the US, and I assume here as well, this is a standard interpretation of quantum mechanics that you learn. So what we want to do is to kind of use the walking droplet, basically use the walking droplet system, develop a sort of pilot wave theory for the walking droplet system. That's what I'm going to describe today. And then the long view would be to try to use that to try to inform something about maybe what's happening at the quantum scale as well. That is something we're not there yet, but that's kind of would be the dream. Okay, so I'll describe. I think I don't want to get technical, so I won't go into a lot of the details. But I'll just say that there have been a number of models that try to describe the behavior of these walking droplets. This is a lot of text on this slide. It's kind of ugly, so I won't go through it in detail. There's a review article that I wrote with my advisor in Reports on Progress in Physics that came out about 5 years ago that has a lot of these details. This is basically to say, so basically you have a bunch of different models. There's a question of whether you model the vertical dynamics, that's the bouncing of the drop. Do you want to model that or not? So some model it, some don't. So for example, this one is no vertical dynamics. Then there's a question of what is your model for the waves, right? So when the drop bounces, it generates waves. How complicated do you want to make that model? So you can assume that the waves are Bessel functions. You can assume yeah, you can assume something much more complicated, like a quasi-potential model. I won't describe what that means, but basically they're more complicated models. So essentially what I'm trying to get across is that there's a hierarchy of models that have been developed that also have a hierarchy of computational times, right? So some of them are very expensive, like this one takes, quite a long time to run, whereas some of them are quite cheap. They can essentially run at the same time scale of the experiments, or some of them even faster, right? So there's a number of different models that people have developed to try to understand the dynamics, and it depends on what effect you're interested in. So today I'm only going to talk about one of these models. It's of course my favorite one because I developed it. So this is the so-called stroboscopic model, and I'll explain what I mean by that. Of course, it doesn't get everything right, but it allows you to capture many of the behaviors in experiments. So the idea is as follows: you basically say that, okay, first thing I'm going to do is I'm going to forget about the bouncing motion. This is of course a crime in many scenarios where the bouncing motion matters, but I'm going to pretend that that's okay. And I'm going to say that, okay, I have something that's generating waves of wavelength lambda f, which is known. This is basically the Faraday wavelength, and these waves decay in time according to some timescale Tn. This can also be estimated. The reason that waves decay is because you have viscosity, right? So it's a viscous bath. So you generate a disturbance, eventually it'll disappear. And now, basically, once you have that in mind, you're kind of forced. Yeah, go ahead.
So usually on the surface we have zero viscosity.
Ah, interesting. So, okay. So, yeah, interesting. So, one version of this, I think, is that you have dissipation in the bulk, and that basically generates a thin boundary layer near the interface. And this is interesting you bring this up, because this is actually the basis of another model, which I don't use actually here, but it's a more sophisticated model, where basically that dissipation in that thin layer appears as a dissipation in the boundary condition. So as you said, the boundary condition usually is just the kinematic and dynamic, right? So there's no dissipation there. But when you take into account that dissipation in the bulk, you can essentially transfer it. I know it's a little vague, but yeah. Yeah. Maybe afterwards I can. I don't think I have any slides on it, but I can write it down. It's yeah. So this is but that's actually the basis of a kind of a better model that people have developed, which I'm not going to use for this problem at least. So basically, once you write that down, you essentially are stuck. So you can say that your disturbance, you're in 2D, right? Because your surface is 2D, is a Bessel function centered at the drop location, decays in time, and like I said, these are Faraday waves, so they oscillate at half the forcing frequency, right? So omega 0 is the forcing frequency. And the interesting thing here is that this time scale you can also estimate. You can write down what this thing is. Now, the main point is that we call this thing the memory time because it dictates the amount of time that the waves persist. And the main point is that it increases as you get closer to gamma f, as you get closer to the Faraday threshold, right? So basically, as you shake harder, the waves last for longer time, right? And the waves become more complicated then. Okay, that's basically it. That's the model. And then from there, it's all very standard. So then you say, again, I'm not modeling the vertical motion, right? So I'm only looking at the motion in the plane. Then my equation is just mass times acceleration of the drop. I have some drag. The drag comes from air drag, and then also when the drop impacts, it loses some energy. That's an interesting fluid dynamics problem. I'm not going to go into it. That was written down in this paper by Jan Moleček and John Bush in 2013. So they figured out what this drag coefficient should be. So then you have the drop being driven by a force that's the gradient of the wave field, right? And the picture there is that if the drop lands on an incline, there's a horizontal component of the force that pushes it. If it lands on something that's not inclined, then it gets no force. Great. What's nice though is that this H is something that the drop itself generates, right? Because the drop itself, as it moves around, it generates this H, and this H is exactly what I wrote down previously, right? It's this Bessel function centered at its location, multiplied by this exponential. You might notice that the time oscillation is now gone because the drop is bouncing at the same frequency as the oscillation. so it never actually sees the oscillation, right? It basically samples a particular point on this wave. This is kind of horrible to look at. So next approximation, you replace the sum by an integral. So you basically say that instead of looking at discrete impacts, I'm going to take a sort of high frequency approximation where I replace the sum by this integral. So I have a continuous source. Basically, I think of the drop as a continuous moving source of standing waves, right? So this thing continuously generates J zeros that all decay in time. So the picture there is that in the near past, these J zeros matter. And then as I go further and further back, I have this exponential decay. So I don't really care about what happens really long time ago. But what I mean by long, of course, is determined by Tm, right? Tm sets that time scale. Okay, so you put it in and you get an integral differential equation, right? So mx double dot, mass times acceleration, so that's the inertia, drag, and the force depends on the drop's entire history. And like I said, of course, you don't really care about the whole history. You care really only up to a time scale Tm, but you do care about some of the history, right? So if you were to evolve this thing in a numerical scheme, you'd have to keep track of the drops past as well. So the way I think about this is the following. So I've just rewritten the problem now as two separate equations, but it's the same thing. The way to think about it is instead of this, I'm modeling this, right? So this is a video that Dan took as well, and it's basically this video, but he's now strobed it at the bouncing frequency, so it's a trick. So you don't see the bouncing, but that's really what this model is doing, right? This model is ignoring this impacting nature of the drop, and it's looking at the continuous time motion instead. Okay, so what is the one of the first things this model was used for is this experiment. So this was a great experiment done originally by Yves Couder and Emmanuel, that's published in PNAS in 2010, and then it was done again in John Bush's group in 2014. So what you do now is, if this system isn't complicated enough already, is you take this whole thing and you put this thing on a rotating table. So this is your rotating table. So remember, this thing is shaking and it's now rotating at the same time. What is the point? So this is a trajectory of a drop. You see it does this kind of complicated looking thing. Oops, that's the answer. So it does this kind of complicated thing. But then when you process the data in the rotating frame, right? So now your lab is turning, but your experiment is stationary. The drop is actually just doing circles. So this is quite nice. So you can ask the question basically, what is the radius of the circle, right? How big is the circle how big is the circle as a function of the rotation rate of the bath? So this is what you get. So in low memory meaning the waves die very quickly. So when I say quickly, I mean within about 4 bounces, the wave field is exponentially damped. You get something kind of boring. Basically says that the radius of the orbit decreases with the rotation rate. So if you spin slowly, you get relatively large orbits, and then as you spin fast, the orbits get smaller monotonically. This is not very interesting. It's kind of the classical, if you like, prediction. So you can basically write down the balance between inertia and Coriolis force. And this is more or less what you'll get. So the dashed line is what you would get if you did that. You'll notice that the data is not on the dashed line, but I'll claim it's close enough. That's a story by itself that I'm not going to go into. But it turns out you can rationalize this offset as well. But what I want to say here is that in the low memory regime where the waves are not important, you don't really get much. You essentially get the classical stuff. In middle memory, though, the picture changes completely. So this is where your waves are decaying about 16 bounces. So the dots here are the data points from the experiment, and the curve is the prediction of the theory. So what I haven't gone into here is how we get this. So I told you what the strobe model was. It turns out from the strobe model, we have a whole kind of theory for finding solutions to the model and analyzing their stability. So this is kind of this was a whole thing by itself, and I won't go into the technical details there, but you can read about them in this paper and the previous paper that I mentioned. So here the color scheme is blue are orbits that are stable, red are orbits that are unstable, and green are orbits that are non-linearly stable. So they have oscillatory instabilities that can saturate. And if you look here, basically, you have this strange behavior where the curve is broken, right? So up here, you have this continuous branch of points, but then it breaks and you have more data here, and then more data here. So it's this discontinuous set of solutions now. And the theory tells you that really what you have is you have a continuous set of solutions, but the stability alternates, right? You have a stable branch and then an unstable branch where, of course, you don't have any data because it's unstable. So the picture here is that you have, oh yeah, and you can also prove actually that these states are all unstable. So the picture here is that you have orbital quantization. This is one of the hallmarks of quantum mechanics, right? This is one of the early problems that people do when they take quantum mechanics. Quantization of orbits in a hydrogen atom or in Landau levels. This is the Landau example. Here you have quantized orbits, but they occur for a very kind of simple in some sense reason that they are just occur because you have instability, right? Linear instability of an orbital solution prevents these solutions from being accessed. So then you have quantization on the Faraday wavelength. The picture gets even worse as you increase the memory even further, worse or better, depending on your viewpoint. So this is in the high memory regime. Now the waves are decaying on a scale of 25 bounces. There it turns out you get a whole bunch of green solutions. So they're green, if you recall, are the orbits that are unstable to oscillations. So we call those wobbling orbits. Up here again, you still have stable orbits. You still have the red unstable orbits. But now even these orbits, the error bars are from the experiments. So even you see these in the experiments as well. Even those orbits become unstable and they start to fluctuate. This is interesting because it turns out as you further increase the memory, then the trajectories become non-circular. So not only do they fluctuate, so you don't get small amplitude fluctuations, you get huge fluctuations and you get this kind of mess, right? You get like spaghetti. But you haven't lost all your structure, it turns out, because now you can ask, what is the radius of curvature of this trajectory? That also looks like a mess. But now you can ask, what is the statistical distribution of this radius of curvature? Right? So you basically, is the radius of curvature as this drop moves around, is it random? And it turns out, no, it's not. It has peaks, again, quantized on the Faraday wavelength. Right? So you have these discrete peaks separated by roughly, in this case, half a wavelength. So this was also observed in the experiments. So this was a set of experiments that Dan did, this was really nice. So you can ask now, basically, what is the statistical distribution of this radius of curvature as a function of the rotation rate? So these are 3 different experiments, 3 different rotation rates. So here you have 3 peaks occurring at large radius, 5 peaks at intermediate radius, 3 peaks at small radius. This again, just to clarify, is experiments. So these are long time experiments to answer your question, hopefully ergodic, of this thing in a rotating, the drop in a rotating frame. And you can basically stack all these histograms in this plot as a function of the orbital radius. And you can see what you get, right? You get this kind of quantized behavior, but it's a statistical quantization, right? It's not sharp. You have this kind of smeared behavior where you do have some orbits that access these intermediate regions, but they're just small, right? They're low probability events. And the high probability events, again, occur at these radii. And this you can recover in the model as well. So this is the model prediction. And again, same story, right? You basically have you have regions where you're likely to find a drop with certain radii of curvature, and then low probability regions in between. So this is the picture. This is the picture in the walking droplet system, at least, that at large memory you have chaos, you have chaotic trajectories, but the chaotic trajectories still have this kind of quantized structure, right? So this is a dynamical view of where quantization comes from, right? At least in the walking droplet system. Then you could get another, so I'll go through this kind of quickly. You can get something that, so you can get these kind of self-orbiting states. So this essentially, these emerge from symmetry. So you can get this is the curve that I showed you previously. There's now a mirror image of this curve that occurs at negative rotation rate, right? It doesn't matter if you turn the bath that way or that way, of course, right? So you get the same, basically the same set of solutions. It turns out though, as you increase the memory, these two branches collide. They cross, on the omega equals 0 axis. So omega equals 0 means that you have no rotation. So this is very strange, right? This says that the drop will go in a circle even though the bath isn't moving. So this is only theoretical. So they looked in the lab, but they couldn't find it because the theory actually would say that this is unstable. So it's not so unexpected. We've predicted though that there is a regime, and I don't have time to go into what that means, but there is some regime in which you might be able to see these states, these self-orbiting states, where the drop goes in a circle even though there is no applied rotation. And if you look carefully, you might notice that this branch of stable solutions, the blue solutions, splits into two as you increase the rotation rate. Right? So omega equals 0, again, is where these stable orbits live, and then they split into two. And this, if you squint, is kind of like an analog of the Zeeman effect. So you have something called Zeeman splitting in quantum mechanics, where you have a degenerate energy level at 0 magnetic field that splits into something of higher energy and something of low energy, depending on the spin. And similarly, in the droplet system, you have two orbits, one that goes clockwise, one that goes counterclockwise. And then as you start turning the bath, one of them increases in radius, one of them decreases in radius, right? So you have like a level splitting effect that occurs in the droplet system. Again, this is purely a dynamical phenomenon, right? Basically due to the forces on these two different orbits. So basically a lot of different quantum analogs have come about from looking at the Strobe model in the rotating frame. So I think the remaining time I have, I want to go to this. So I'll go through this kind of quickly. So what about boundaries? So everything I've talked about right now is the drop is just by itself, right? The drop is not interacting with any barriers, except for the tunneling, which is what I talked about in the very beginning. This was one of the first experiments that was done, and this was kind of one of the most striking ones. This was a diffraction experiment. So this is one of the first examples we learned about in quantum mechanics, right? Where you have a particle that basically electrons diffract. So this was essentially the same idea as the tunneling experiment, except now you have two barriers. You send a drop through the gap in between them. So this is a single slit experiment, and you see that the drop kind of deviates. You play the same game that as in the tunneling experiment. You ask what is the statistics of the eventual angle at which the drop goes, and you get this kind of wave-like kind of oscillatory behavior, right? So the drop likes to do something like diffraction, was the claim in the paper, right? That you get different angles that are preferred over others. This was a very exciting paper. The problem was that it attracted a lot of attention, so there's a big list of papers here, and a number of papers tried to understand this experiment, redo it, but they all seem to get different results. So it's a difficult experiment to do. This is where Giuseppe came in. So Giuseppe, Dan, and John Bush's group, they did, I would say, the most careful experiments on this subject. And they basically found actually that the fluid system, in some sense, is not nice. So in the fluid system, you don't actually get something that looks like diffraction. So I'll draw your attention to this plot here. So horizontal axis is the angle at which the drop goes. The vertical axis is the probability of seeing these different angles. At low memory, you get something kind of boring. You get basically the peaks at two preferred angles. But even at high memory, where you hope to see something like diffraction, so your trajectories they look kind of promising, but you don't really get wave-like structure. It's hard to really see what you get. And basically the problem is that these two barriers, they act as really strong attractors, and the drop essentially gets deflected too strongly by those barriers. So you lose, if it's there at all, you basically don't see diffraction-like behavior. So this was kind of disappointing, I think. But the question then we asked was, is it possible to imagine kind of a different system or a related system where you could see diffraction, but with the same pilot wave picture? So this is, of course, very difficult to do experimentally because you'd have to do a million different experiments to try to probe different conditions. But it's a perfect example for numerics. So we used, in this case, the Strobe model, essentially the same model I talked about previously. But here we represented the barrier as a bunch of discrete sources. So basically we put down a bunch of points on which the wave field is 0. this is what the experiment is trying to do, right? Because you put these barriers down, but because it's a hydrodynamic system, you actually don't know what the boundary conditions are on the barrier. Actually, maybe even the notion of boundary condition doesn't really make sense because it's a non-local system. But in the numerical problem, you can enforce the boundary conditions exactly. And that's what we did. So basically, you enforce the condition that these barriers are perfectly reflecting. And then you ask, how does the drop behave as it moves through? So the results I'm going to talk about were published in this paper in PhysRevE. This was done with Giuseppe Ali, Alessia Chirimella, and then Giuseppe, of course. And I think it was quite nice. So what you end up getting, so first we tried a simple problem, the edge. So here you can think of it as it's the slit, but you take away one, right? So now you just have an edge. This is the wave field. This is the same wave field, just viewed from the top, so you can see kind of what the ripples look like. You send a bunch of different drops through this thing. One goes that way, one goes that way, etc., etc. You do an ensemble of simulations. You do a bunch of different trajectories with different initial conditions. And you can ask yourself, what is happening here? So what we think is going on, at least the picture here, so this is a picture of the wave field generated by the sources only. So I've subtracted off the contribution of the wave itself. And do you see how it kind of freezes? I'll try to pause this thing at the right time. I don't think I'm quick enough, but let's try this. So there. So you see, as the drop goes through, the wave field temporarily freezes, the wave field due to the sources. And that actually is what deflects the drop, right? So the drop goes through, the barrier essentially is generating a wave profile that guides the drop either left or right. That's kind of the cartoon. So the picture you end up getting is this one. So here I've color-coded the trajectories based on essentially where the drops end up. Some of the details don't matter, but you have basically a red through blue. And notice that you have these kind of beams of trajectories that you have a uniform distribution of trajectories down here. The drops are going upwards, and then as you get near the edge, the drops kind of funnel into these little regions, and you get this wave-like behavior in the drop trajectories, right? So this is like diffraction. Basically, you have waves that are generated at the edge that then somehow influence the way the drop is moving. And we can rationalize that by looking at 4 different trajectories. This one goes eventually to the right. This one is a little bit different. This one goes to the left. This one goes to the right. This one goes to the left. So you have this periodicity basically, right? So as you have different trajectories that go, some go to the left, some go to the right, and eventually you end up with this kind of diffraction pattern. So this is because we have control over the boundary conditions in this setup. So this was the eventual result. So this is for the edge geometry. So this is the probability of finding the drop at a given location in the plane. So there's the edge. This is all downstream of the edge. You can see the diffraction in these kind of bright beams. So you have regions of large probability where you're likely to see the drop. This is the result from quantum mechanics. And you can see that they have some at least qualitative resemblance, right? So you have diffraction from the edge. You have a region of large probability here, and then you have these beams that go outwards. It's a little bit more clear if you look at the probability on a screen. So imagine now putting a screen at this location, and you ask, what is the probability of finding the drop at different locations? Here you have this oscillatory behavior in the droplet, and you have the same oscillatory behavior in quantum mechanics as well. Differences, of course, are that here you have much faster decay because the waves decay faster in this than in quantum mechanics. That's, because you have a hydrodynamic system here. And then there's another detail that the oscillations here are on half the wavelength, whereas in quantum mechanics, they are on the de Broglie wavelength itself. That, I don't have time to go into why, but we have a reason why we think that's true. So I think now I'll jump to the kind of the last part of this, which was, yes. Yeah. If I go back?
Yeah.
Yeah.
In the classical experiment, you have the barrier submerged.
Yes.
So technically, when the waves pass through the barrier, you have a modification of the wave speed.
That's right.
In this case, it's different because you have the pillar which is infinite. So you don't have the perturbation to the local velocity.
Absolutely.
and so it's a different experience.
I agree. And so that's a very good point. And so this, I think we don't quite understand very well yet, but this, I think the perturbations in the speed, amongst maybe other things, there are like other effects also. And I think all those things actually conspire to make that actually not an ideal system in which to study diffraction. Because what ends up happening, the outcome of that is that basically the drop gets attracted towards the barrier at a very specific angle. So the pillar, if you could somehow make the pillar
Because a strange competition between the dispersion and nonlinearity in the fluid.
in that region, I think so. I think that's right. Whereas the pillar somehow, if you could do the pillar experiment, these simulations suggest that you could actually get something nicer, right? You get kind of nice wave-like behavior. Yeah. So I'll kind of end on this. So then we did the slit experiment. So this is what we were kind of going after. This is again a video of what's going on. So you see you have a bunch of trajectories. One goes left, one goes right. You know, you can do it again, an ensemble of different trajectories depending on their initial position. This is the result that you get. So here I've color coded again, this time the trajectories by their final angle. But you can kind of see here that you have big, strong deflections of the trajectories behind the edge. And you have this, again, periodicity in the different, the way the trajectories go. So some of the trajectories go left, and some next to it go straight, some go to the right. And then this pattern continues as you change the initial position of the drop. You can again look at this behavior statistically. Maybe I'll skip to this one here. So you can basically ask what is the probability of finding the drop at some distance on a screen at some distance as a function of its impact of its initial position. So here I've shown here two different simulations with two different sets of boundary of pillars, if you'd like. This is a bit of a detail, it doesn't really matter. But the point is that in both cases, you get this behavior where you have oscillations on the Faraday wavelength, and the number of oscillations increases as you increase the size of the slit, right? So you have few oscillations here, more oscillations here, even more oscillations for the longest slit. And this was, I think, about 10 wavelengths in size. Same behavior, of course, in quantum mechanics, right? So for narrow slits, you have few oscillations, more, and then even more. And if you look at the patterns, I think qualitatively they look quite similar, right? So you even get some kind of more higher order qualitative similarity between the two. So it seems like in a statistical sense, we've recovered something that looks like diffraction behavior in a single slit system. Okay, so I think I'll conclude. So basically, I wanted to say that there's, I think this is an interesting system that's kind of worth studying. And there've been a number of models that have been developed to try to untangle the behavior of the walking droplet system in different geometries and in different situations. But there's still a lot that can be done. So here I talked about one model, one kind of simple model. That's the stroboscopic model. And we use it to study quantization of orbits in a rotating frame. So there we saw that you can get something like orbital quantization, but in a dynamical sense. Then we used it to understand the deflection of a walker by barriers, and that was to get things like diffraction past an edge and diffraction through a slit. And in the near field, at least, you get things that seem to resemble the results from quantum mechanics. So basically, if you're able to control the boundary conditions on these barriers, then this dynamical picture seems to match, at least qualitatively, what you get from looking at waves purely. So I think this is a kind of an exciting venture, and using kind of more sophisticated theories or alternative theories that go beyond the experiment is an interesting endeavor. And then eventually, of course, to try to match things with the predictions of quantum mechanics. That'd be very useful as well. Thanks very much for coming.
So is there any question?
If you put the pillar randomly, you can localize the wave function.
That's a good one. So I didn't have time to talk about it. So that was an experiment done quite recently. So this is something like Anderson localization. Yeah. So this was in Pedro Sainz's group at UNC Chapel Hill. So what they did I think they didn't use pillars. I actually don't remember why.
The topography is round, so the bottom of the block is round. That
But it goes above the surface.
No.
below,
Below,
but that's
okay.
in that case you match the Anderson maximization prediction.
You get something like Anderson Loop. It's interesting you say that because if I recall correctly, the original idea in Eve's group was to do what he suggested, right?
Yeah,
It's
so they
like
tried
pillars.
like many years ago in Kuda's group, and I think it was not so convincing the result. And then they kind of abandoned the fight. And then several times this group
Did it with the topography, yeah.
with the topography, the different.
Yeah. I don't remember why the pillars didn't really work, but it's a tricky experiment.
So this is very nice presentation.
Thanks.
So it seems to me, if I have understood well, that there is a problem with boundary conditions.
Yeah.
I mean, in the sense that you don't quite understand how to make, let's say, the analog of a screen. When you consider a screen in diffraction.
Yep.
A screen is a place where the wave function goes to zero, or the pilot wave, or whatever wave.
Yeah, that's right.
But it goes to zero.
That's right.
Okay, then you can turn problem backward and say, okay, let's go and look if there are experimental cases in quantum mechanics where the screen is not really a place where the wave goes to zero, but because they're
interesting.
This oscillation wave, let's say pilot wave.
Yeah.
It, in reality, in the experiment, it does have non-zero amplitude on the screen.
That's right.
So perhaps there is an example in quantum mechanics of diffraction or interaction with screen that is not a perfect screen.
Yeah.
And then that would match better the experimental results. Is it something
that's interesting
to do?
Yeah, you should say it.
To my knowledge, the diffraction behavior is quite independent of the boundary conditions in general in optics throughout quantum mechanics. At least in the practice. And so maybe the short answer to your question is that I think the hydrodynamic system is just very specific, and it's very strange what is happening, as Francis was suggesting, that no linearity is because we have a changing path. I don't think it can match any of the quantum or optics because the behavior there seems to be very consistent despite, even if you change the boundary conditions substantially. So, to my knowledge, then there can be experiment in very specific case. The majority of things are independent. It's qualitative.
It's an interesting idea, though.
I was thinking more of diffraction in optics because there you have an array of different materials and you can really choose what the electromagnetic field does inside the material.
That's right. Yeah.
Zero in a metal, it can be different from zero in a dielectric.
That's right.
Material.
That's right.
So you can have even exotic materials where you can really tune.
But there is the answer also from theory, right? Because the Kirchhoff.
Yeah.
No,
yeah.
So it's not a well-posed problem mathematically, because even if you use different boundary conditions in the far field, right, you get the same result.
But in the near field, no.
The near field is less clear.
Is yours near field or far field?
The match is best in near field.
In the simulations.
When you compare the simulations against the predictions of quantum mechanics, and the reason there, I think, is because in our simulations, we're trying to do something sort of like the hydrodynamic system, but we just change the boundary conditions. And in the hydrodynamic system, you have dissipation, right? So if you go too far, you basically don't see the barrier.
Other questions?
I have a comment. Okay. It's not more of a comment.
Yeah, please.
I can wait for the questions.
There is another question. You want to make the comment now or later?
Yeah. It's not a joke, right? Because this is the first time that I discuss about these things with, especially with Giuseppe. And every time I attend this kind of presentation, I have the feeling like imagine a scene where you have kids playing on a playground with a nice ball, and then you go and see, oh, look, it's a nice ball. Let me see what it is. You have it in your hand, it's an atomic bomb. And the atomic bomb is that you're actually, testing quantum mechanics here. You're developing analogs over analogs over analogs. And so where is this going? I mean, imagine if you can push it all the way, all the way to the prize. And the prize here is, and do you think that you can prove quantum mechanics wrong or prove it right? I mean, what would be, the experiment that really tells you, I've made an experiment that proves that we've been reading, we've been doing science wrong in the last century or not.
Yeah.
You see what I mean?
Yeah.
This is nice, that's
Sure.
a lot of different directions of expansion.
Sure.
There's really one thing that really beats into my mind.
Right.
It's okay. Suppose you can have all the analogies, but where do you think this will break? The quantum phenomenon that really you cannot produce because that would mean that you win the Nobel Prize.
Right. So I think it's a good question, and it's something that we've stayed up too late many times talking about it. So I'll give a kind of a non-answer for a non-question, exactly. So I think so right now we're still at the stage, right, where even the theory that we have doesn't really match. I mean, it doesn't have a quantitative match with quantum mechanics, right? These qualitative similarities. Suppose one is able to develop, right? So the first step would be if you could develop a pilot wave theory, a mechanistic pilot wave theory that perfectly matches existing experiments on quantum mechanics. That would be great. But then again, I think the Copenhagen school essentially would say, so what, right? Because the current theory of quantum mechanics also does that, right? So then it's kind of a matter of what do you like better? And me personally, I like trajectories, right? So, and I think most of us do because we grow up looking at throwing balls, right, and stuff. So we like the notion of trajectories. But somebody could say that that's just a human, right? I'm injecting my own bias into this. So I agree with that. Or I don't know about agree, but I hear what you're saying. That part of the difficulty here is that I think for now, there isn't really an experiment that, to my knowledge at least, that basically the theory of quantum mechanics does not capture that.
Should we go back to EPR paradoxes, belts, inequalities, and all these kind of things? Isn't it that the price of all this?
That's right. So, and I think that's actually some of the more exciting directions in which this program is going. So I agree. So entanglement, at least as far as I can tell, there isn't an experiment that has gone against what the theory of quantum mechanics says, but it's still very unintuitive and strange, I think is fair to say. So if the droplet system can produce something like entanglement, and then maybe that could tell us kind of what's going on, I agree that'd be very exciting. So I didn't have time to go into it. There is a paper recently that does something like tries to do something like a Bell test, but I can't really comment too much on it because I didn't work on that and I don't know kind of the details of it that well. But I know that's like an active area that people are interested in. I agree that that's like a good place. Yeah, that's an interesting place to go.
So maybe if I can add very quickly, the point, at least for me, is not that to prove that quantum mechanics is wrong, because I like it also. And I think it's correct because it matches a wonderful way of experiments. But the picture that these experiments and models suggest is that it could be possible that to obtain. So, okay, maybe not the picture. So what is the question? So to which extent quantum mechanics could be an emergent theory from an underlying classical chaotic Faraday system? So I have a classical chaotic Faraday system. To which extent I can go and derive a quantum mechanical result as emergent from this underlying chaotic. So I think this is the right. This for me the right way to ask the question. Okay, so I have
so you shift the probabilistic side of quantum mechanics from something that is really, really fundamental to chaotic theory. So you assume there are fluctuations of thermodynamic reason or something else, but yeah.
That's right. That's right. This is what this suggests. That actually,
a different type of.
It's a different type of, and the probability is coming from somewhere else, right? It's coming from chaos in this sense. Yeah. And in principle, just to add to that, I think in principle, if this is true, right, that quantum mechanics is basically an effective theory, then there should be, down the line with some technological developments, it should be possible to do an experiment to actually distinguish, right, to basically see that. So, but that's,
this would be huge. This would be the most important finding in science in 50 years.
50 years.
500. Yeah, right. Exactly.
Okay, thank you again.
Thanks very much.
So if you have more questions, there is time to meet him during the refreshment outside.